Good morning, good afternoon, everybody. I hope you can hear me well. Thank you very much for Energy Simulation for organizing this event, and thank you all for attending. I'm talking today about the model-based and data-driven reservoir management through digital fields concepts. This is the topic of our current energy simulation chair. It's a preparation to use reservoir simulations in digital field analysis. And the main motivation came from industry because they told me that the reservoir simulation models are very often used for life cycle analysis, but they are not really being used for short-term decisions. So we decided to investigate since last year to investigate if we can use these reservoir simulation models in real-time applications. And if we are successful in that, we can use them in digital field analysis as well. So the group is called Unisim, Reservoir Simulation and Management. Our focus is in reservoir simulation and providing education, innovation, methodology, and new software related to reservoir simulation and reservoir management. We have not only reservoir simulation and engineering, but also we have a strong integration with geoscience, production engineering, economic evaluation, and nowadays also data science. So our objective of our mission is to improve the decision-making process using reservoir simulation models. Now also we are using data and special tools like optimization techniques and so on. The focus is the reservoirs of the pre-salt and offshore in Brazil, which have very high investments, low flexibility, and long-term projects with complex decisions. We want to add reliability and quality for these studies using reservoir simulation as the main tool, which normally requires a high computational demand and also normally requires a high number of simulations in order to have higher chance of better decisions. As we have also an increase in the computational time, we are trying to develop techniques to speed up the process, with some techniques to speed up decisions and multiple runs management in multi-fidelity approaches. And nowadays, since last year, since the beginning of the simulation chair phase 2 that we are dealing with, we are trying to apply this methodology to short-term forecasts and decisions. So I'm presenting very briefly the concepts I presented last year about the closed loop field development and management. We are putting an F here because we are integrating not only the reservoir, but also the surface facilities. And so it's fields instead of reservoir. And we are trying to develop a technique that is applicable not only for management of the fields, but also for development of the fields, because many of the pre-salt fields are in the beginning of the field's lives, so it's in development phase. The idea is similar to several companies and several industries that work in this model-based closed-loop analysis. In our group, everybody is working in this concept here. We divide our activities in 4 colors. The first color is dedicated to build the model, which is the green one here. We take the data from the reservoir, and with this data, we build the high fidelity models, the most fidelity we can to reproduce the fluid behavior and fluid movement behavior in the reservoir. But of course, depending on the study objective, and also include the uncertainties here, that's why we have multiple boxes here. But depending on the objectives, we cannot take too much time to wait until the decisions are made, because these high fidelity models take a long time to run, sometimes hours, sometimes days. So we are developing techniques to simplify the models, like the ones that Sebastian Geiger showed today, or even low fidelity, medium fidelity, or high fidelity models, that we call a fit for purpose models, which is the model that have the best relationship between the quality of the results and the time we have to wait for them to run. And also they have to be fast enough to be included in this probabilistic approach. Once we have the models, we have to verify if they honor the pass. We have this red part here, which is related to the pass, which is the data simulation. We don't call history match in our group anymore, because our objective is not to match the data. The objective is to use the data to reduce uncertainties of the process. And we want to keep the variability of the future in order to have the future with the high ability we believe we have. And then we have the future here, which is the blue color. The future can be the life cycle future, where we try to find the best production strategy for the field, consider the entire life of the field, and also including the operational noise here to avoid bias in the results. And until last year, that was the production strategy that we were planning to introduce in the field here, to implement in the field. And after we implement this introduction, we can measure the effects by well production, fluid movement, seismic 4D, and so on. And we keep going. That's why it's a closed loop. Since last year, we are trying to work on this black part here in the top. And I will not show too many results this year. I will show the ideas. Probably next year, we're going to have more results about that. And the short-term behavior and forecast and decisions will be taken in this black part here in the top. So this is the focus of the decisions, and the black part is the focus of the short-term decisions. I'm showing in this picture the same thing as before, but I simplify the green part here and the red part here, and also the blue part here, and focusing on the black part here. The idea is that the life cycle optimization can give us an idea and how the reservoir can be controlled. We call this set points. And we'll have the set points for long term until the end of the reservoir's life. But once we go into cycles, we can change these set points and go to real controls, which are really how the wells will be controlled, how the field will be controlled. And we can do this in a shorter cycle. We don't need to do that for the entire life of the field, as we're going to show in some ideas here. So the focus of today's presentation is this black part here. We have divided the parameters, optimization parameters, or the variables in three groups. Group one is the development variables. We call design variables, those that we decide to develop the field, like the platform capacity, the number of wells, position of wells, and so on. The group two is the management control variables, which we call group two here. And group three are the revitalization variables, which for the pre-salt fields are important. That's why we included them here since the beginning of the reservoir's life, because the reservoir of the pre-salts are planning to do waves. And the second wave, for example, we're going to have new wells and so on. So we have to plan these new wells since the beginning. But the focus for the black part, in order to do the black part, we divided this group two in three categories. The group two for life cycle, those are the parameters that we optimize the entire life of the field, which we normally do when we do life cycle optimization. And then we created these two new type of variables, the C variables, which are cycle variables that we are going to analyze in the next cycle, and the short term that we are going to analyze in the real time. And we also include the operational noise that for short term will be very important. I try to summarize what we are doing in this new picture here. The idea is to have cycles like we have here in the top. We change the cycle every time the models are not good anymore to reproduce the behavior of the field. So that's this red part here, the data simulation. So every time you do a data simulation, we have a new cycle. The life cycle optimization that we call here, we can optimize G1, G2L, or G3 here, depending on when they enter in the field. So G1 since the beginning, G3 and the second wave, for example, and G2L are the controls for the entire life. And then once we have the optimization of the life cycle optimization, we are going to have the black part here. The black part is the cycle and the short term. For the cycle, we are going to concentrate our analysis in the variables that we can change within the cycle. So as we have less variable, we can use less time to optimize, simple optimization methods, and better control rules for the cycle. And once we do this, we go to short term where we implement them in the field. So that's the whole idea of the change we are doing. The plan was to do that since last year, but since we started, we have observed that the simulation models that we had were not good enough to do that. So we had to change a lot of things in our procedures. And we are trying to show a little bit of our implementations from last year to this year. The first thing that we detected is that the models that are good for life cycle are not very good for short term, especially in the transition from the past for the future. I'm going to show some graphs here to show what I'm doing. Another thing is that the integration of production facilities are much more important for short-term forecast than for life cycle, because for life cycle, we can reproduce an average behavior for the reservoir. But for short-term, we need to have the exact behavior to change the wells and change the controls. So the integration will provide us a better estimation for forecast conditions for the cycle. And also, we have to go much deeper and understand the difference between the control variables, separating which is physical restriction, which is reservoir management, operational problems, and so on. Because for a life cycle, we can put all together in the simulator because they have the same effect mathematically for the reservoir. But when we are trying to optimize these behaviors, these controls, we have to separate these effects. I'm going to show a little bit of this in the next slides. Once we finish all this, we are in the middle of the process now. We are also in parallel studying data-driven techniques, trying to improve the short-term behavior, as we're going to see in some slides here, but probably we're going to present something next year. So in other words, we are reducing the size of the cycle, and we are going to have shorter cycles to have better decisions. Other things that we are doing is that we are observing that the typical analysis that we do for life cycle, which is probabilistic approaches using a lot of uncertainty and so on, may change when we go to short cycles, especially that many of the uncertainties will not be important in the next cycle. And also the fidelity of the models can be different because again, for the life cycle, we can reproduce an average behavior, and for short term, we need an exact behavior. So we are performing a multi-fidelity analysis, and we can change the model when we go from one to another. Now I'm going to show us a series of results we have in intermediate steps. Here is an example showing how an example of the behavior of the data simulation process and why we have to change the cycles and how good are the models in the short term. Here's historical data in the future. In gray, we have the data before the history matching, and after the data simulation here is in blue. And even after data simulation, we have here in the right the number of models that are good. So we have 50 models after 4 months that are still good to reproduce the behavior of the reservoir. And after 5 months, something happened. For example, the water breakthrough happens in a certain well and so on, and the models are not good anymore. So it's very important for us to detect this moment and change the models. Otherwise, the short-term models will not be good. Another thing that we observed is that from the transition from the past to the future, we have a very important role of the productivity and injectivity of the wells. This is an example of how bad this can be the problem before history matching and after history matching here. But even after history matching, we still have a lot of uncertainty in the rates in this case, almost 100% difference. And this may be a sector for life cycle because in the long term, the material balance will accommodate the results. But for short term, we cannot have results that wrong. The same thing that I showed there, I'm showing here probabilistically, showing that if we don't do anything, we can have results like this, where in the left part here, we have the history part where the data seems to be very good, but when we go to the forecast, which is this part here, the results are not good because of the productivity and injectivity of the wells. So we have to change all this productivity, injectivity to correct this, and probabilistically, because we have 100 models and sometimes more than that to do it. Another thing that we observed and we corrected, we already know that the production facilities are not perfect. The models are not good. We have error also there. We can see here in the left part. This is a function. This error in the forecast is due to the errors in the calculation of the production facilities boundary conditions. So we are performing a data simulation procedure also of the model for the production facilities. So the model of the production facilities will have to also reproduce the past. And once we correct this, we have, in this example, a much better result and much better forecast for the future. This is an example and how bad can be this type of data in a real world, in a real field where wells are being closed and the rates change every day. We have change in bottom hole pressure almost every day here and every month, and the rates change a lot. And this is the history, and we have to forecast the conditions here. What I'm saying is that for long history, for long forecasts, we can maybe put an average behavior and an average boundary condition. But for short term, we have to go deep into the production facilities. We have to calculate the operational conditions here very well and try to use these operational conditions in the forecast. So here's just to show how difficult can be this type of thing in a real case. So we have to be careful with these details. So once we do all this, we try to separate the variables in three categories here, as I showed. The life cycle, we try to reproduce the human intervention-free forecast, where we try to reproduce the behavior of the reservoir, considering the reservoir potential and the production facilities constraints. Once we have this, we go to the second step, which is the reservoir management, which are intentional controls to reach determined objectives, which are our control rules or set points here. And this is the life cycle optimization. Once we have this, we go to the cycle optimization, what we call here. We try to improve the results for the next cycle. And once we improve the results for the next cycle, we go to the short term, as we reproduce here from the figure there. And in the short term, we have to include all types of problems like unmapped uncertainties, like changes in oil price, operational problems like random problems that can happen in the wells, in the platforms, and so on. And we have to be ready to correct these problems. Once we have all this, we are going to integrate. We are doing this research in parallel. We are going to integrate with data-driven. The data-driven model will try to correct the very short-term forecast for models when the models are not so good, as I showed in the previous slides. And as data-driven is also not perfect, we are using the model-based with uncertainties to set up boundary conditions for the data-driven analysis. So one technique is helping the other to improve the decisions for short-term. And once we finish this, we are going to decrease the size of the cycles and then go to real time. So that's our plan for this phase of energy share. So to conclude, the idea here is to change what we were doing before in the closed loop model-based analysis. We changed all four colors here. I'm summarizing the changes here. In the green colors, we not only change the models to improve the quality of the short-term forecast, but we also are introducing some multi-fidelity analysis here. So using our models with different fidelities for each objective. In the red part, we had to make a lot of changes in the data simulation process, especially to improve the transition from the past to the future. Nowadays, we have several techniques to do that, to improve this behavior. And we also have introduced the data simulation for the production facilities. So if we are reproducing the behavior of the production facilities in the near past, we have better chances to reproduce it in the near future. That's what we are trying to do. In the blue part, we divided this problem in three categories, and we are applying this optimization process in three different steps. It can be like a hierarchical optimization, for example. So first you optimize the G2L, then you go to G2C, concentrating the analysis of the parameters that we can change in the next days or next weeks or months. And then once we have this, the best way we can, we go to react to the changes that we have in short term. That's the idea. And in order to do that, we believe we are going to have this multi-fidelity approach. The model that's very good for G2L may be different from the model that's good for G2S. So we are going to have changes in the models in the middle of the process. And once we do this, again, we are trying to apply this to the real time, which is the companies are asking us to do. And what we believe is going to happen is that we are going to use also probabilistic approach, but not the way we use for life cycle. We don't have to consider so many uncertainties in the short term because many of the uncertainties don't have shorter term effects. And our focus is still on this methodology, pre-salt fields with permanent 4D and intelligent completions and logged CO2 injections, and what we call gas-driven optimization because we have a lot of restrictions in the production system, especially for gas production. With that, I would like to acknowledge first my team, the team that's working hard to put all these things together. We are in almost 80 people today in several projects with companies, and also the sponsors that help us to put all this research together in all these parts of the closed loop. With that, I finish my talk, and I'm glad to answer any questions if you might have.
Thank you very much, Dr. Schiozer. I guess while we're waiting on people to type in questions, if any, I suffice to say that this is extremely important piece of work. Not only that you need to make predictions for the long term, but also a little bit more accuracy, certainly for the short term. Any mistakes made in making predictions for the long term, it costs a lot of money when you're dealing with a prolific offshore reservoir, where the geology may be uncertain, the FPSO, how many do you need, and all that kind of thing. So thank you very much for the talk. Again, if there's any questions, please type it in. If not, we would certainly would allow a little bit more discussion at the end of the day for a 30-minute live chat among the presenters and the attendees. So yes, there's one question from Xinjia Zhao. So yeah, he thank you for your presentation, and he's got a question about the short term. Does short-term production mean that the observation time of the simulation is very short, or does it mean that it is time-dependent problem and a transient process?
Very good questions. Because when we say short term, there is no default definition. Each company is using a different way, and each university is doing different way. We have an internal document in our group where we define what's really short term, and for us, short term is the cycle. For example, from 1 day to 6 months. So that's what we are trying to do in this G2C optimization here. But you are right. If you want to go to real time, we have to decrease this short term even more, like days, because then we have to put the models to work in a very day-to-day decision. For example, if something happened today, I have to use the models to react tomorrow, for example. And then we have to have this shorter term. So we are defining short term in our case, because we are in the middle of the process trying to define the G2C before, because if you are not successful in G2C, we cannot go to G2S. But what we are asking is about the G2S, which is the much shorter. It's like a transient. We want to get there, but we are not there yet.
Okay. Thank